Give me a moment. Okay, let's get started. So, is it recording? Yes. Okay, so let's get started. So again, I set your quiz 2 on Friday. I think it starts at like 1 or 2. 1 or 2. So it's gonna be on cyclic groups and permutations. Yeah, so I think he should be going over permutations on Friday. So permutation, nothing theoretical. Yeah, I'll just ask you like what's these two cycles equivalent to, right? Like the 1 goes to 6, 6 goes to 3, that stuff. And then cyclic groups. We'll do problems on cyclic groups today. Maybe harder ones, right? So any questions before we start? Okay. So let's go back to cyclic groups because I didn't really define something important. Sort of skipped it. So given a group G, and given an element A and G, the order of A is the smallest positive integer n such that a to the n is the identity. Yeah. So it's the smallest positive power you take such that you get the identity, right? And then we write the order of A, which is n. Yeah. So if no such n, so if you keep taking powers and you don't get the identity, like never, if no such n exists, then order of A, we say it's infinite, yeah? Or notation is this. So let's do some examples, right? In Z mod 12Z, I just picked 12. The class of 1, what's the order, right? What power of 1 eventually, what's the identity? The identity is 0, right? The class of 0. So how many powers do I have to take until I get 0? Anyone? 3, 4.5. 4.5. Oh, 4.5 is like, did you have the problem number? Sorry, I thought it was like problem 5, but like, do you have the problem number? Yeah, I could do that. Yeah, sure. I was planning on doing the harder ones first, but yeah, okay. So what's the order of 1 here? So how many powers of 1 until I get 0? Yeah, sure. So again, right, 1 squared is 1 plus 1, which is the class of 2, right? 1 cubed is this, right? So how many times until I get the identity, right? You'll see it's 12, right? It's 12. So the order's 12. Okay. Yeah, it's 12. So now let's do another example. What about the class of 2? How many, what's the order? What's the first time you get the identity? So you just count count until you get 12. 2, 4, 6, 8, 10, 12. So it should be 6, right? Because 2 to the 6 is 0. Everyone clear? Yeah, but note that you see from here, like 1 to the 24 is also 0, right? Because it's if you like, it's 1 to the 24 squared, which is 0 squared, which is 0. Yeah, by square, I mean, hopefully the law of exponents, right? So, but note that order is the smallest one, right? We want the smallest one. So you just keep taking powers until you get the identity, and then that's your order. So moving, is everyone clear? So next example, what's the order of 1 in Z? So again, hopefully it's implied by now it's addition. What's the order of 1? So how many times do I add 1 until I get 0? It's kind of like a trick question. So yeah, it's infinite, right? You're never gonna get 0. So the order of 1 is infinite. Yeah. Okay. Now, but no, for finite groups, you will get it is finite order. So you could show that. So now there are some propositions. I write proposition. I'm not sure if it's theorem or proposition in the book, but let's just say proposition. Subgroups of cyclic groups are cyclic. So that's something we'll use in our, I guess later on. But the more important property is if order of G is n. I mean, n is just arbitrary number, right? It's just in other words, the group is finite, yeah? So it's not infinite. It's not infinite like the integers here, right? So, and G is cyclic. So with A as generator, So in other words, G is, I'm just calling the generator A. And A to the K is E. Then A to the K is E, if and only if and only if n divides K, where so really quickly, let's see. You don't even need to know the proof, right? I mean, maybe you do. You might get tested on it, but it's pretty simple, right? So what's the order of A? If A is the generator, of G. What is this? If A is the generator of G, what's the order of A? We have explicit value for it. It's the order of A is actually n. Yeah, because if you think about it, it can't be less than n, because if it's less than n, you're not going to generate the whole group, right? For example, like if let's assume, I don't know, like let's just example, order of G is 6. If A cubed is E, let's say the order is 3, then you can't generate the whole group, right? Because you have A squared, A cubed, this is the identity. So what's A to the 4th? A to the 4th, this is just A cubed times A, but this is the identity, so you just get A back, right? So this is redundant, right? So you see here, you only have three distinct elements, right? A squared, and A cubed. you have nothing else, right? So on. So hopefully that convinces you that, like, if you generate the whole group, you can't have orders smaller, right? Yeah, I mean K right here is K is not like a fixed number. It's just saying if you raise A to some value K and you get the identity, this is a proposition, right? Then N must divide it. So in other words, like here, I'm claiming, right? So A to the 12 is E. So here, 6 divides 12. Yeah. So I'm actually claiming you cannot have any value smaller. Yeah. So I'm saying, like, K will have to be bigger. This proposition, right, basically says K has to be bigger than N, bigger than or equal to. Yeah. It can't be smaller for this reason. Right here, right? If you have something smaller, you will not generate. If you have something smaller and you raise it and you get the identity, you will not generate the whole group, right? Because you only have 3 elements. Are you clear? I don't know what capital K is. Okay. So hopefully that's clear. Yeah. So this is pretty important, right? I mean, you see here, right? Like, for example, the order here is 12. So, and then here I raised it to 24 and I got 0 as well. So 12 divides 24. Yeah. And then I don't know why I wrote in black, right? Like here, 1 to the 36 is also 0. And from here, 12 divides 36. Yeah. So this is your explicit example. So if you raise, so later on we will see that this is not only for cyclic groups, but if you raise an element to some power, K, and you get the identity, the order must divide it. Yeah. So, but in this case, since it's cyclic, the order is N. Yeah. But so that later, this is later. So generalize, I'm gonna just write generalization later. It's called Lagrange theorem. Yeah, but we haven't learned that yet. So okay. Okay, moving on. We have a notion of what all the other elements are, the order of all the other elements. So if absolute value of G is N, G cyclic, a generator in particular, so order of A is n, and we let B be a to some power, yeah? I don't know what k is, it's just arbitrary, yeah? B is a to some power. This is, let B, and this is certainly true, right? Because if B is just an arbitrary element of G, if you like, right? Because any element of G is some power of A. So it's a to some power. Then the order of B is n over D, where D is GCD of K and N. Yeah, so in particular, order of B divides N. Yeah, I mean, it's some, I mean, this is an integer. So in particular, it's some number that divides N, right? Okay. Now, really quickly, we could generalize this now. So everyone follow? So if G is Z mod NZ, right? Right, let's apply this theorem. If G is Z mod NZ, order of G is N, right? G is certainly cyclic, it has 1 as a generator. So question, which elements are generators of, in other words, can you find another generator, right? So 1, if I let B be 1 to some power k, Ren is B a generator of G. Yeah? So let's apply the theorem, right? What does it mean to be generator? Well, what's the order? It means that the order is n, right? You generate the whole group. So order of B using the theorem is n over D, where D equals GCD of K and N, right? Remember, B, this is order of A to the K, or 1 to the K in our case. So you want GCD of K and N to be co-prime, right? You want this to be 1. Want D to equal 1, right? Because then order of B is n over 1, which is n. So you generate the whole group. So that tells you what it is, right? It's everything co-prime to n. Yeah. So in other words, if G is Z mod 12Z, right? 1 is a generator clearly, but any power co-prime to it is also a generator. So what's co-prime to 12? 5, what else? 7, and then I think 11. I mean, these are all of it, but this is just the class of 5, the class of 7, and then the class of 11, right? So let's just check it, right? 5 to the first is 5. 5 squared is 10. 5 cubed is 15. 15 is 3 mod 12, right? 5 to the fourth is, what's 3 plus 5? 8. Right? So, and then 5 to the fifth is 8 plus 5 is 13. So 13 mod 12 is 1. Hopefully you are all convinced by now. So 5 to the 6th is 6. 5 to the 7th is 11. 5 to the 8th. So 16 mod 12 is 4. You know, so on and so forth, right? I should not have chosen such a huge number. 14 is 2 mod 12. 5 to the 11 is 7. And then 5 to the 12 is 0. Yeah. So you see that 5 also has order 12. And then you can check 7 and 11 too as well. Yeah. So using this theorem, you see that in Z mod NZ, it's clear 1 is a generator, but anything co-prime to n. So the class of A generates Z mod NZ if and only if GCD of AN is 1. Yeah. So this is like a corollary. Pretty cool, right? Anything that's co-prime to your number generates your whole group. Everyone clear so far? Everyone good? Okay. So with that in mind, let's do problems together. So we're going to start doing actual theoretical group theory problems because I feel, but let's do the hard ones. and then after I do the hard ones, we'll go over the homework. Yeah. But we're only going to do it as a class. Yeah. So, I mean, maybe let's do something easy. Let's do 11. Yeah. If A to the 24 is E in a group G, so if A to the 24 equals E in a group G, what are possible orders of A? Right, so first off, first question, can it be larger than 24? Yes or no? Can the order of A be bigger than 24? Yes or no? No, right? Because I mean, even if I raise some number, right? If the order was bigger than 24, that would contradict the smallest part, right? So remember, the order of a group is the smallest, right? And if I raise a bigger number and I get E, it doesn't really matter, right? Because I raised 24 and I got E. So I know that it must be smaller than 24, smaller than or equal to, yeah? Or it could be smaller, but what numbers can it be? Yeah. So it's clear any divisor of it will work, right? So like 1, 2, 3. Oh, I'm bad at this. 6, 8. 8 times 3. Yeah. Okay. 12. Right. These are all possible, right? Because if the order is like 3, right, then it's clear that the identity times identity is identity, right? So, right, for example. Now, so the question becomes, can it be a non-divisor? No, why? By the way, you don't have to chat. You could like unmute yourself if you. It might be faster that way. So, for example, like why can A to the 5? Right? Why not this?
I guess it can generate the whole group.
No, no, it's so here the G is not, G need not be cyclic, right? I mean, they're not. I don't think they're assuming that. Yeah, they're not really assuming G is cyclic. Oh, by the way, I don't mean this, right? Like this is possible, but I mean like, but I mean this. This is what I mean. Sorry. And a, I mean, because like an a squared, a cubed is not e. Yeah, because I mean, if a was just the identity itself, any power of the identity is the identity, right? So this is what order means, right? It's the smallest one. So this just means, you know, this by itself doesn't mean order, right? It just means you raise to some power, you get identity. Order means like any power smaller doesn't give identity, right? So how can you use this? So let's see, right? If a to the fifth is e, how can I write 24? I can write 24 as a to the fourth. Yeah. Hopefully I did my math right. And then this is e to the fourth. So this is just a to the fourth, right? But this is equal to a to the 24. And we know a to the 24 is the identity, right? So contradiction, right? Because if 5 was the order, it would mean a to the fourth is not e, but here we got a to the fourth is e. Yeah. So if anything not like, you know, not a divisor, you can reduce it, right? Using the 24, you could reduce it, and then you get something smaller is not, and then that's something smaller that would contradict order, right? Because yeah. It's division algorithm, right? So if k is less than 24 and k does not divide 24, you can long divide and to get remainder, right? To get remainder, r, let's call it r, yeah, r, and then, and you know remainder is always smaller than your original number, right? Like you know, when you do this, the remainder is smaller than k, right? Then a to the r is e. So, you know, contradiction, right? Like here, the remainder when you divide 24 by 5 is 4, right? So that's why you have the 4 there. It's long division. So everyone clear on that, or see how it works? So here you don't even need G as cyclic. So again, maybe I did not write that. Yeah, it's just 11 and just in a group G, right? So
is that proposition like applied to non-cyclic group?
proposition.
I mean like the a to the k equals e even only if n divides k, that proposition.
Oh, for now it's Yeah, I mean that is only for cyclic groups.
Only for okay.
Yeah. I mean later on, if you like, we can go Lagrange theorem. Basically, the corollary 6.11 is the strong thing. Yeah. But that's later. Yeah. If G is, let's say it's finite, so it's, absolute value n, then order of G must divide n. But that's later. You can't use that yet.
Oh no,
So,
there's a proposition like in section 4, like in the
yeah,
sine
yeah,
x subgroup.
yeah. But that's only for cyclic groups.
Oh, I
So
see.
yeah, yeah. This one is for like any group, right? If you recorrelate 6.11, it's not just for cyclic groups. But sadly, you can't use that now. So, is everyone clear so far? We could move on to maybe harder ones. Okay. So ZP has no non-trivial subgroups. So if P is prime, right? So why is that the case? ZP has no non-trivial sub. So this is, ZP is, yeah, P prime. It's some people use this notation. Some people use this notation. It's better to use the second one I wrote, but P is prime. Show Z mod PZ has no non-trivial subgroups. Has no non-trivial subgroups. Okay. So from here, what do you know? So why is this the case? So we have the proposition, right? Let's use the proposition, right? And then, so we know that, we know Z mod PZ is cyclic, right? It's generated by 1. So from the theorem or proposition, subgroups of cyclic groups are cyclic, right? So in other words, we just have to check why, given an element, if it's cyclic, it's generated by some element, right? So given arbitrary element, non-identity element, that's what non-trivial means. It's not just the group, given by E, given arbitrary non-identity element. Why consider, I'll call it B. So B is like 1 to the, because 1 is a generator, B is just 1 to some power, right? Let's call it 1 to the K. Consider the group generated by 1 to the K, right? You take all powers of it. Why is this not a non-trivial subgroup? So subgroup, I think by yeah, but I guess non-trivial also means you're it's not proper. Yeah. So from here, right, let's use the order, right? What's the order? Order of 1 to the K. This thing is, again, it's N divided by D, where D is GCD of, P divided by D, GCD of P and K. Now, question, what's the GCD of P and K? P is prime. So what's the possible divisors of a prime? If I gave you a prime number, what are the possible divisors of it?
P and itself. No, Y and itself.
Yeah, 1 in itself, right? Can it be P? It would mean P divides K, right? But what is 1 to the P? This is 0, right?
Yeah.
Agree? but we said non-identity. So you see, it has to be 1. Agree? So I mean, to be pedantic, to be pedantic, like So it has to be 1, right? So in other words, this has order P. In other words, it generates the whole group. Yeah, because the whole group has order P. So you see that there's no non-trivial subgroups, right? Because any element will generate the whole group. For example, I mean, other than identity, right? You could test it like Z mod 5Z, like any element, like 2, right? 2 to the first is 2, 2 squared is 4, 2 cubed is 6, right? 6 mod 5 is 1. 2 to the 4th, well, I don't know why I did that. 2 to the 4th is 3, and then 2 to the 5th is 0, right? And then you could try it for the numbers. So in other words, this is generated by 2, the class of 2. It's also generated by the class of 1, also by the class of 3, also by the class of 4. Yeah, anything but 0. So there's lots of generators for Z mod PZ, right? When P is prime. Everyone good? Let's do like one more. I mean, one more of like the ones I look up. Okay, let's do 27. Let's just do 27. If G and H have orders, if G and H have orders 15 and 16 respectively, what is order of G intersect? What is order of G intersect H? So from here, right, maybe it's better to take an element, right? Take non-identity element in. So again, when I write this, right, that's assuming there is a non-identity, but if there's no non-identity element, then the order is 1, right? It's every group has the identity. There's always just the trivial group, just the group with the identity. So here, let's take a non-identity element. Let's call it B. Call it B. So question. So B is in both, right? Because it's intersection. So B is in this. Now this group is cyclic, right? It's, I mean, it by definition is cyclic. It's generated by G. It's the group generated by G. So B is G to some power K. Yeah. So what does the proposition tell us, right? I have a cyclic group, I have an element. What's the order of B? What do you know? Again, what's the order of G? 15 divided by D, where D is GCD of K and 15. In particular, right? Order of B divides 15, right? So what's the possible numbers order of B can be? 1, 3, 5. Oh, sorry, I don't know why I wrote 7. 1, 3, 5, 15, right? Everyone follow so far? Okay, on the other hand, I am in H. H is 6, B is H to, I'm running out of letters. h to the j. So order of b is is 16 over j, or d, where, sorry. I'll put d1 here and then d2. d2 is GCD of 16 and j. Now, in particular, order of b divides 16. So order of b must be 2, 4, 8, 16. Yeah? Or 1.
You missed one, yeah.
So what's the order of b, everyone?
1.
Yeah, you have no choice, right? it has to be one, but if it's none of these overlap, right? The only overlap is 1. And what element has order 1? You only have a single element in your group that has order 1. What is it?
Itself.
I need each of the 1 to be identity. So what must B be? B must be the identity, right? No other element to the first power is the identity, unless you are the identity. So you see here that from here, the order of, since every element, this is an arbitrary, so I get a contradiction, right? Because it's non-identity. But you see that if I take any element, the order must be 1. So you see that, this is just the identity group. So from here, let's summarize, right? From here, we took an element here, and using the division property, right? The order must divide the order of G and order of H. I get that the order must divide 15, and the order must divide 16. And the only number that works is 1. And the only element of order 1 is the identity. So there is a generalization to this. I think, let me try to find it. Right here. If you read problem 30, it's a generalization, yeah? If order of A is M, order of B is N, and GCD of M and N is 1, then the intersection is identity, yeah? So in our case, M was 15, N was 16, right? 15 and 16 are coprime. So GCD of 15 and 16 is 1. So the intersection must be the identity. Yeah. So this is problem 30 is like a generalization of problem 27. The argument's completely the same though, except you don't use.
What if like the GCD of Mn is greater than 1? So the order can have multiple choice. So we will choose the smallest one as the order of the intersection.
I mean, it'll depend. Like, how do I say this? Like the order can be. I mean, all you know is that it could be the identity, or it could be something bigger, right? Like if the GCD is not 1, like, I mean, I can come up with examples where the intersection is not the identity, but I can come up with examples of where the intersection is the identity. So,
so what if the question asks like the order of the intersection of two groups? What's the answer? Do we have to list all the orders, like all the options?
So what I mean is there shouldn't be if G is an arbitrary group, and then it would depend on what the group is what I'm saying. Like, yeah, like I mean, just do something like, let me think. Right, like Z mod 8Z, the group generated by 2 and the group generated by 4. the intersection is just the group generated by 4, right? It's not the identity. Not equal to identity, right? It's the intersection is the group generated by 4, right? Because it's a subgroup. Right, this thing has order 4. This thing has order 2. Yeah. But I'm saying it's possible it can be the identity. So you haven't learned, I don't know if you learned Cartesian product groups yet. So I don't want to go into that, but just to convince you, yeah. There's something called Cartesian product of 2 groups. You know, the operation is whatever the operation. In this case, it's plus. I'll do it in general, but in this case, it's both plus. But like, if this is star and this is like circle, then the operation is like component-wise, like AB, and then CD is A star C and then B circle D. Yeah, but in this case, it's, you know, since it's both under plus, the operation is given by both by plus. So like AB operation CD is A plus C, B plus D. Yeah. And if you consider the subgroup generated by 0, 1, and the subgroup generated by 1, 0, this has order 2, right? This thing order 2. Because 1 plus 1 is 0, right? 2 is 0 mod 2. And then same thing here, this is order 2. But the intersection is the identity. So basically I'm saying the answer depends on the group, right? Like here, it's not coprime, but the intersection is not E. Here, it's not coprime because GCD of 2 and 2 is 2. But in this case, it is the identity, right? So I'm saying that there's no like set result. It will like depend on what your group is. But does that answer your question? Okay. Can anyone tell me what homework problem you need me to talk about? Can you give me the number? Anyone? Because I don't know the number. So can you give me the problem number? 3.417. Wait, is this actually 4.5? Because someone said 4.5. So like I'm confused. So you don't want me to do so 3.5. I mean this one? The symmetries of a square? Is that what you want me to do? Oh, okay. 3 examples of groups with 8 elements. How about this? So groups with 8 elements. I went over 1, right? I'll leave this to you. So I gave you 1, right? D4, the symmetries of a square. Remember, there's 4 rotations, 4 reflections, right? And then there's Z mod 8Z. That's, you know, remainders mod 8. And then I can go over this, but if you take all the coprime elements, they form a group under multiplication. So like Z mod example. So this is unrelated to question. Unrelated to question. If you do Z mod 8Z cross, right? This means the the set 1, 3, 5, 7, right, under multiplication, right? These form a group, right? They call this U8. Yeah, so I'm saying consider U16. This has 8 elements. Now you can argue this group. Now the only thing left for you to do in homework is argue why these 3 groups are different, right? I mean, they could sort of or do they? Yeah, see, different groups means like, you know, I guess they're different because they're, you know, by different I think they mean like there's not an isomorphism that preserves group properties between them. But I guess different, you know, you argue, right? This one is cyclic. Yeah. So you argue that these 2 are not cyclic. Agree? And then here, right? So for here, what I suggest you do is maybe argue by order of elements. By order of elements. So here, I believe, like, you know, this one, reflections are order 2, right? Because if you reflect and reflect, you get the same thing back. So you have 4 reflections, order 2. You have the identity rotation, which is, you know, identity order 1. And then you have the rotation by 180 degrees, right? Rotation 180 degrees is order 2, right? Because if you rotate 180 and then 360, you get the same thing back. And then I believe rotation 90, 270 is order 4, right? Because if you rotate 90, then 90, then 90, then 90, you get the identity back, right? And then same thing for 2, and then you argue, right? So this one has 5 elements, order 2, and 2 elements, order 4. And I think this one, if you just calculate it, right? Like 3 has like order, I believe 3 has order 4. For example, you just calculate the order of every element, and then you'll see that there's there's more elements of order 4 here. Of order 4. So you know these 2 are different. Yeah, sorry, not U8, U16. T4 and U16 are different. Z8 is clearly different. The Z8 is cyclic. The other 2 groups are not. But to argue the other 2 groups are different.
For the same question, can we also use like the example of S8?
S8.
S8. Like we have different.
You mean this?
Yeah.
No, because the order of this is 8 factorial. Times 6 times 5 times 4 times 3 times 2. Like the order of S3 is 3 times 2 times 1. The S8 is big. It is not a group of order 8.
Oh, I see. Thank you. Oh, for the and for the 4.5, can you like do the third one?
4.5.
Like the third one, like 3C. So you have to list all the subgroups, like
So again, subgroups of cyclic groups are cyclic, right?
Yeah.
So just consider the power of the group generated by 2, 3, 4. Some of them will give the same, same thing, but 6. Sorry, I forgot 5. But 5 generates the whole group because it's coprime. But right, you know it's cyclic, right? So you know it's generated by 1 element. So because subgroups of cyclic groups are cyclic, So just consider the powers of each element, and then you'll get all the subgroups. It's not that.
And another quick question is like I was a little bit confused about the notation. Like sometimes you use like the generator when you do the like 1 to the power or like 2 to the power. It is like 2 to the power 2. It's like 4, and sometimes you write like, you know, sometimes it's addition, sometimes it's like multiplication.
It's what the group operation is, right? So I'm saying like in this case, Z mod 12Z, it's a group under addition. So the operation is addition.
So when you're writing Z, is it like assume that it is already addition or like
But I mean, I'm saying it doesn't make. I mean, you know it's addition because multiplication. I mean, yeah, I guess it is assume it's addition, but it can't be multiplication because this is not a group. Like this thing under multiplication is not a group. There's no inverses, right? Like what do you multiply to 2 to get, 2 times what gives 1, the class of 1, like nothing, right? So like this thing has like no inverses, no invert. Let me say some elements have no inverse.
So when you're writing this notation, it's like basically it has to be a group, so it can be like a multiplication.
No, when I write this, so given group G and operation circle, when I write like given G and G, G cubed is G, whatever the operation is. So in my example, it's this Z mod 12Z under addition. So 1 cubed is my operation is, you go with the operation, right?
I see.
Yeah. Any other questions? Right, because in order to have a group, you need an operation. so like whenever I write like cube or square, it's whatever the operation is. So if the operation was multiply, then it's multiply. If the operation was plus, then it's plus. But sometimes the book doesn't write it because really like this is the only way you're gonna have a, it can't be multiply. So in the case where like your set doesn't form a group under multiplication, they sometimes just write this. It's sort of implied it's plus because it can't be a group under multiplication.
Okay, thank you.
Yeah. Okay. Okay.